Hello, so this video is kind of a follow-on from the last video. It's kind of like a part 2, I suppose. And it's actually introducing this new theorem called Abel's theorem. So basically, if you remember the last video, we were talking about this whole idea behind linear dependence and linear independence. Okay, and we basically finished off the last video that if we had, two solutions, y1 and y2, okay, we could verify we could verify whether they were linear dependent or linear independent. The Wronskian would be equal to this thing. Wronskian would be equal to this thing. So we've got our two solutions on the top row, then the derivatives of solution on the bottom row, and we take the determinant of that. Okay. Well, if they're linearly dependent, if they're linearly dependent, then effectively a cancellation occurs, and we end up with because one can be written in terms of the other. When we take the determinant, there's a cancellation which occurs. So therefore, we should get the Wronskian should be 0 because of that cancellation. Whereas if they're linearly independent, the Wronskian is not 0. Okay. Now the thing is, with a two-dimensional kind of system like that, it's not really too bad. A lot of the time, the Wronskian isn't too bad. But what if we've got quite a nasty function that we have to differentiate? So say, for example, if one of the solutions is kind of really, really nasty and it can look really nasty to differentiate. Okay. Well, basically, this is where Abel's theorem comes in, because it allows us to determine an expression for the Wronskian. Allows us to determine an expression for the Wronskian quite nicely. So it's based on kind of an integrating factor, basically. So let's suppose we have, that we have a differential operator. Remember what a differential operator is. It's just really a function, but it can't call it a function because instead of putting values into a function, we're putting functions into that function. So that's why we call it an operator. But if you think operator function, okay, there is a second order differential equation. So plus a of t times y dash plus b of t times y. Okay, and let's just consider it as a homogeneous operator. So in other words, the right-hand side is 0. Okay, and let's suppose that we can get some value. We can get some solutions out of this. So y1 and y2. So y1 and y2 are the solutions to this operator now. Okay, and basically what we do is we assume that a and b are sensible. Okay, so what do we mean by sensible? It means continuous on some kind of interval, some open interval. So basically there's no kind of jumps, there's no discontinuities, there's no gaps in the function. You can just draw the function without taking the pen off your paper. Okay, so that's what a and b are. They're just sensible functions. Okay, then basically we can say that the Wronskian is just given by some constant times by something which looks remarkably like the integrating factor, except of course the integrating factor works with first order equations, differential equations. Here we've got a second order differential equation, but it looks incredibly similar because we just take the second part, if you like, the derivative of y. The coefficient in front of the derivative of y, and we stick it up here. So it looks, hopefully you can see, the integrating factor is mu. So if you have the integrating factor is if you have this thing, so first order differential equation, okay, the integrating factor is given by mu equals e to the integral of this coefficient here, so p of t dt. Okay, well here it looks remarkably similar. You can see they look remarkably similar. So but basically the Wronskian is given by that. Now, I'm not going to go into a proof of where that all comes from and stuff. We are going to do perhaps an example with it, maybe. But we're not going to go into a proof of where it all comes from because it's not really necessary here. Basically, this is just the idea behind the Wronskian. Now, the thing is with this constant, when we do the proof, if you do the proof, you're interested in proof and stuff, then, you can see that this constant effectively only depends on y1 and y2. It's just some function of y1 and y2. So basically, when you find an expression for this constant, it will just involve y1 and y2. It won't involve t. Now, that's really important because basically what it means is this c is kind of, it's only dependent on y1 and y2, not t. So t won't affect it. Now, look what we want. Look what we want from the Wronskian. We want to see whether the Wronskian is either 0 or non-zero. Okay. So in other words, if the Wronskian is 0, so if the Wronskian is 0, so if the Wronskian is 0, then that basically implies that c e to the integral of a of t dt, okay, is equal to 0 as well. Well, look. look what we've got here. Look what we've got here. The exponential, an exponential to any power, so e to some power, let's call it e to some power, let's call it n, can never be 0. It can never be 0. It's always got to be positive. It's always got to be positive. So therefore this, what we've effectively got here is we've got two things being multiplied together to make 0. So therefore one of them has to be 0. At least one of them has to be 0. Well, that in there cannot be 0. That whole thing there cannot be 0. Right? So therefore the only way that the Wronskian is 0 is if c is equal to 0. Now c doesn't depend on t. So changing t won't make a bit of difference to the value of c. Okay, changing t won't make a bit of difference to the value of c. So in other words, the only way that c can be 0 is if y1 and y2 are somehow set up in a certain way to make that constant to be 0. Okay? Now, we're not going to go into everything where it comes from and stuff. This is just really talking about it at the moment. Okay, and likewise, if the Wronskian is not equal to 0, then that implies that c must also not equal to 0. Okay? So, so this is basically the idea. The Wronskian, if the Wronskian is 0, then that implies that c must be 0. Okay? And if the Wronskian is not equal to 0, then that implies that c cannot be 0. Okay? So you may say, well, okay, Abel's theorem, fine. It's just another way of getting the value of the Wronskian. Yes, it is. It's absolutely that. But the thing is, the idea is that if you've got kind of some difficult y1 and y2 to work with, or if you can't find the solution for y1 and y2, okay, you don't have to kind of try and solve the differential equation. You don't have to try and solve this thing in order to get y1 and y2. Okay, that's kind of the idea behind it. I know C will be based on that, but even if you can get close, if you can, all you have to basically do is determine that y1 and y2 won't make C 0. So in other words, you don't even have to solve it, and you can get the value of the Wronskian. So that's kind of a nice little trick. So let's do an example. So let's suppose we have y double dash minus y equals 0. So remember what we have. We have the we have y double in general, where is it? This thing up here, okay, and the Wronskian is given by that thing there. So I'll just write that out for you. And so the Wronskian is just going to be c times e to the negative integral of a of t. Okay, that's all there is to it. So let's suppose we have this. Well, obviously, if we compare this to this, then what's a of t? What is a of t? Well, a of t will be 0, right? Because this is really just y double dash plus 0 y dash minus y equals 0. Okay, so a of t is really just 0, okay? So therefore, what we've got here is that the Wronskian is c e to the integral of 0 dt. Okay, well, what's the integral of 0? It's just going to be 0. Okay, the integral of 0 is 0. And so therefore, we've got e to the negative 0, so that's just going to be 1. It's just going to be 1. So therefore, we're just left with the Wronskian. It's just equal to c. So in other words, it's just some number. Now, if we compare it with, so that was really simple. So basically, we can immediately see that they're linearly independent. Okay, because Wronskian is just going to be equal to some number. Now, at the moment, we don't know what that some number is, but we just know that it is going to be some number that's not 0. Yeah? So therefore, we know immediately they're linearly independent. So that was really quick. Okay, now if we compare it with the traditional way that we usually do it, so we got y double dash minus y equals 0. So now if we compare it with the traditional way, so in other words, we have to find what the Wronskian actually is. Well, first of all, we need to solve it. So we need to go r squared minus 1 equals 0. This is the difference of two squares, so it's r minus 1 and r plus 1. So therefore, the two solutions that we're going to get, so we're going to get, r1 is going to be equal to 1, and r2 is going to be equal to minus 1. So therefore, we seek a solution of the form y equals e to the rt. So therefore, y1 is going to be e to the r1 of t, so it's just going to be 1t. Okay, and y2 is going to be e to the so r2 of t, so it's just going to be minus t. So therefore, these are our two solutions. Okay, these are our two solutions now. So now we're going to form the Wronskian. Okay, so already, normally we'd be finished by now with the Abel's theorem. But here we've got Wronskian is going to be y1, which is e to the t, and y2 is e to the minus t. And then we've got to differentiate it to find what the second row of the Wronskian is. Oh, my word. So imagine, if these are two things that are difficult to integrate, difficult to differentiate, already we could be kind of it could already be taking some quite long time. So this is going to be e of t. This isn't too bad, to be fair, but I know I'm just trying to make the point that, you know, we could have something that's really difficult to differentiate. Okay, so what's this going to be? It's going to be minus e to the t times e to the minus t. Okay, minus e to the t times e to the minus t. Okay, so this is going to be, well, it's going to be minus e to the t minus t, so it's going to be 0. Okay, minus e to the t minus t, so, you know, I'm just using power laws, I'm just combining this into one thing, so it's e to the t minus t, so therefore that's going to be 0 as well. So we've got minus 1, so therefore that's going to be minus 2. So the Wronskian is minus 2, which is non-zero, so therefore linearly independent. Look how long that took. And in actual fact, you know, with the Wronskian up here, we knew it was going to be equal to some value. You know, with linear dependence and with linear independence, we're not worried about what the value of the Wronskian actually is, except for the fact that we want it either, where are we? We want it either that it's not equal to 0 or it's equal to 0. That's all we're interested in. So basically, if we can get it out to show, like we did with Abel's theorem here, we just know it's going to be some value that's non-zero. So therefore, we know that immediately they're going to be linearly independent. We didn't even have to work out the Wronskian. Whereas with this method, okay, fine, we did actually verify that the Wronskian was minus 2. So in actual fact, we know now that C is minus 2 from doing this method, fine. But we're not actually interested in the specific value of the Wronskian. We're just interested whether it's 0 or non-zero. So this is why Abel's theorem is so much quicker. So this is Abel's theorem. This is why Abel's theorem is so much quicker. Okay?